Hello, everyone, and welcome to our 93rd free webinar titled Practical Reservoir Simulation, presented by our instructor, Engineer Hisham Mukhtar. Engineer Hisham is our reservoir engineering team leader. Um, Before we start our presentation, I'll make a small introduction about OPA upcoming service and plans. For the first time in OPA, we will conduct two waves together starting this November with Advanced Practical Reservoir Simulation, which will be a live course which will be presented by the same instructor of today's webinar, Engineer Hisham. The course starts this Sunday, so make sure to enroll in it. We will also conduct OSHA General Industry, Power BI in oil and gas, coil tubing operations, carbonate reservoir modeling, PCB design operations and troubleshooting, NMR interpretation, and theory. Our live courses are very interactive. You will also get lifetime access for course recordings. You will be in a WhatsApp technical group for course discussions and inquiries. Even after the course ends, you can ask any question you want. And not to mention the online credential verification found on our website. Here are the course prices. There are original prices and ambassador OPA ambassadors prices. We will know later in this presentation how to be an OPA ambassador. You can scan this QR code to register in our upcoming live courses. Here is our special offer, our super package discount. You can buy 3 courses and get the other 4 for free. So you will pay only $440 and save $480. You can contact us to register in this package discount. We have conducted more than 40 recorded courses, which are now available in sales in reservoir engineering, G&G, rig and rigless operations, production technology bundles. You can also scan this QR code to register in our recorded courses. We also offer a mentorship program. It's a one-to-one mentoring session by highly experienced mentors. It's like a tailored program based on your needs. You can request anything you want, and the requests can include explaining the know-how of a software, guiding on personal data, professional guiding for PhD and master, helping undergrad students in their projects. We have completed more than 45 mentorship program with more than 900 learning hours, and the mentees were from more than 8 different countries. You can scan this QR code to apply for a mentorship program. Here's a glance of our OPA website. It's www.opacourses.com. We offer everything there, whether they are recorded courses, live courses, apply for a mentorship program, or apply for internship, or even joining webinars. So make sure you give it a visit. And finally, how to be an OPA ambassador. There are 2 tracks. You will just take one or more courses or just take a mentorship program. So what will you get from being an OPA ambassador? As you have seen earlier in this presentation, you will get discounts on all courses in the future, and you will also get a group discount when you get your friends with you. Thank you for listening, and now it's time for our session. Engineer Hisham, the mic is yours.
Yes, thank you so much. Can you hear me?
Yes, I can hear you well.
My screen is clear, right?
Yes, very clear.
Okay, thank you so much, and hello everyone, and welcome to this live webinar. I'm Hisham Mukhtar Ali, Senior Reservoir Engineer with about 13 years experience in reservoir characterization and management and simulation. So this webinar is designed to cover a comprehensive overview of the workflow of reservoir simulation, the process of numerical modeling and the comparison between the subsurface modeling techniques, analytical versus numerical, and then the how to unbox or quality check the static 3D models, and then how to define a simulation run for conventional reservoir and for the dual porosity or dual permeability or even fractured reservoirs. So, starting directly with our agenda, starting with the overview of reservoir simulation, QA/QC of static 3D grids, the process of model initialization, what does it mean, and the how to define and the main elements of the development strategy, and then the definition of a simulation run for conventional and dual porosity reservoir models. So, starting with this basic overview for the full field modeling process, we typically have three main elements of the modeling, starting from the reservoir flow simulation to highlight the fluid flow in the porous media. This is mostly maybe by numerical approach like reservoir 3D reservoir modeling, maybe by analytical approaches like material balance analysis and so on. Second element is the well flow simulation. This is to simulate the fluid flow through the well completions to characterize fluid movement by the vertical lift performance model and connect between the subsurface or the porous media to the to link to this subsurface to the surface network. And last element is the network flow simulation. As you can see, this is to simulate the fluid flow through surface pipes and surface networks, considering the constraints of the production network, the dimensions of and lengths of pipelines, and so on. So we have three typical approaches to highlight the subsurface problems: analytical, empirical approach, analytical, and numerical, which is our concern on this webinar. So in this slide, you can find a comprehensive description. So, this is typically the production system. As you can see in the subsurface, we have a particular reservoir with a specific porous media and porosity, rock and fluid properties, and a particular subsurface structure, maybe anticline faulted structure, and so on, as you can see. And in between, we have connecting the this subsurface to the surface network by the well completions. Whatever the geometry of your wells, maybe vertical wells, maybe deviated, maybe horizontal like this, and so on. So to characterize this system, generally we have to involve basic fundamentals or basic principles, starting with the Darcy's law to characterize the fluid flow in this porous media, as you can see, which is the flow rate equation. Then we have to apply also the material balance equation or the continuity equation, which means the remaining volume at a particular time will be the initial volume minus the produced volume. Third principle is the BVT properties or thermodynamic parameters or the equation of a state model, because the fluid properties like fluid density, fluid viscosity, fluid or formation volume factor, and so on, all of these parameters are typically dependent of pressure. So we have to define a particular equation to characterize the fluid properties versus pressure, because the pressure is typically reducing from the as you can see from this point. This point from the average reservoir pressure to the bottom hole flowing pressure. So from this point to this point, we have fluid flow in the porous media. Dawes law must be applied. And to transmit fluid from the porous media to the bottom of the well, we have to involve another model, which is the inflow performance relationship, or the IPR model. And from the bottom of the well to the wellhead, another model must be included, which is the outflow or VLB model, and then the surface network model, as mentioned, to design or to simulate the surface network constraints and conditions. So the operating system of your well maybe will be defined by this nodal analysis plot. It's a pressure versus flow rate in x-axis. So the intersection between two different systems, so the inflow or the IBR to a particular node with the outflow, will be the operating point of your system. Basically, these principles are the same and also valid for the applications of reservoir simulation and numerical modeling. So for the EMB project life cycle, as you can see, we have four different phases, starting from the exploration phase, appraisal, development, and maturity or production phase. In this plot, we have cash flow versus time in x-axis. The cash flow during the exploration phase is typically negative because we are investing more capital cost for the seismic processing and acquisition, exploration, drilling, and so on. Once we have the particular successful discovery, you can start production after the within the appraisal phase to highlight or to get more on the better understanding for your subsurface, to identify the reservoir extension, reservoir size, the fluid contact, average reservoir pressure, fluid distribution, phase distribution, and so on. All of this must be analyzed and characterized during the appraisal phase. So next, which is the development phase or peak oil production. This is the maximum oil production phase for any particular field, followed by the maturity phase. So the role of reservoir simulation is typically very important and critical during the appraisal, which means we are collecting more subsurface data to understand the reservoir fluid and rock properties, and also reservoir geometry and reservoir structure. And also it's very critical during the development phase to define several field development plans or several depletion plans to achieve the ultimate economic recovery. This is mostly the main objective of a reservoir simulation study. So the mission is to achieve the as you can see, we have three different development strategies, is to achieve the ultimate economic recovery with the optimized cost, which optimized running cost. So it's important to achieve the maximum recovery and delay the feed lifetime as much as we can, and also it's to achieve the maximum peak oil for your assets using the optimum development strategy. So back to our three different techniques to highlight subsurface problems. We have commonly used the two common approaches: the analytical approach, which means we have an exact solution to an approximate problem, which means we have some assumptions in this technique, like the material balance equation, divisivity equation for pressure transient analysis, and so on. we have different assumptions. Let's say we assume we have constant porosity, we reservoir pressure is constant at a particular point, and so on. But for the third approach, which is the numerical approach, in that case, we provide more realistic problem because we define sophisticated and controlled distribution of reservoir properties. Like in a simulation model, you can define the properties distribution for porosity, permeability in X direction, Y direction, and Z direction. Also, you can define the fluid contact, you can define structure, fault model, the fluid contact, phase distribution, and so on. All of this can be defined using the actual data. Meanwhile, in this approach, we are iterating the solution by the iterative procedure to achieve the history matching for our actual or measured data. This is the mechanism of the numerical approach. So visible simulation means we have your reservoir will be divided into grid blocks or grid cells, and you have to define basic properties for each grid block and or grid cell, and solve the partial or simulation equation, which are partial differential equation, to get pressure and saturation for each grid block at every time step. So this is you can monitor change in saturation versus time, change in pressure versus time, and so on. And also you can optimize your depletion strategy. So we need this approach to predict the field performance under unlimited, as mentioned before, unlimited development strategies or depletion strategies by setting how many wells will be drilled, what is the secondary recovery technique, do we which one is better, water injection or gas injection, the pilot or testing of the incremental recovery by tertiary or enhanced oil recovery techniques like surfactant flooding, or even polymer flooding, and so on. All of these scenarios can be applied and tested in your simulation model. So a reservoir characterization process, it has three main elements for characterization of fluids and rocks, and also the petrophysical data, which is combination between fluids and rock analysis. All of this will be integrated in one 3D model. Because the recovery process, as you can see, is more complex, more than you can ever expect. It's important to have a valid 3D model to apply different trials and different approaches on different depletion strategies and check the recovery efficiency. So recovery efficiency, as per this equation, we have several parameters, including like the bore scale efficiency and drainage efficiency and connection between wells, also a sweep efficiency in vertical and horizontal direction. Also, we have additional cutoffs, maybe physical or commercial constraints, like the reservoir energy, the capacity of the production and processing facilities, and also you may have some commercial constraints like the prices and the economic rates and so on. So building a 3D reservoir model, as you can see, all subsurface data must be considered to define the reservoir structure, starting from the static model, the 3D surface to define reservoir horizons and zones, and then layers. engineering data like well testing and physical data like well logging, core data, and so on. All of this will be required for physical modeling and the properties distribution. Once we have valid or applicable 3D grid, you can define the rock physics data to define a dynamic model or dynamic grid to start your simulation runs. So the model is, as mentioned before, is to define your reservoir into grid blocks or grid cells. Basic properties must be defined for each grid block or grid cells, like porosity, the effective porosity, directional permeability, net gross, and so on, fluid saturation, and then solve the simulation equation after initializing your model. In that case, rock physics data like relative permeability and capillary pressure data must be defined to initialize the pressure and fluid saturation for every grid block at the initial time step. This is simply the process of simulation model initialization. So mostly we have initial data or 2D or 3D data like structure contour maps, horizons, 3D surface, and so on. This will be plus fault model. Thus, all of them will be used to build a 3D model after definition of basic rock properties. As you can see, net gross porosity, permeability in all in 3D directions, X and I and J direction. So we have initially a geological model to construct a 3D simulation grid or static grid. After in including the engineering data, you can find a dynamic model. Next step is to apply the histomatching to fine-tune and adjust your model parameters to try to mimic the historical data or match the historical data. Once your model is matching the historical data, this model at this time can be used for running prediction and for production optimization, like for the incremental recovery and reducing the operational costs. So the mechanism is we have specific sections in your simulation model or data file. The geological data to define the basic grid properties like porosity, permeability, and net gross, so you can calculate the pore volume and calculate transmissibility and depth. Rock physics data, as mentioned, like as you can see, like fluid contacts, like BVT data or formation volume factor, solution gas oil ratio, and so on, and also the relative permeability and the capillary pressure data to define the all of them will be stored in props and solution section. It means all of this data will be used to initialize your model and calculate the initial pressure and saturation, and also calculate the in-place volume. Last step is to define well operations by the definition of well geometries, well completion data, production data, and the historical data to define a particular development strategy. This will be in the schedule section. So in the schedule section, you will define wells and surface facility and define the time step of your simulator. So simulating the flow, we have, as you can see, like this simple grid. We have flow from one grid to another one. So you have to consider the transmissibility between this grid, for example, to this grid, and so on, because we have one vertical well in this grid. So the flow is typically going in this direction from the upstream to downstream pressure. and then they flow from grad to well completion like this grad, and finally they flow within the well bores and well completion. So basic flow equation is typically transmissibility times mobility and potential difference. As per this equation, the flow rate for any particular phase at any connection like this, it will be a function of the transmissibility of this connection, which is function of KH, the transmissibility thickness product, and also the completion efficiency like scan factor and well-bore radius, and also the mobility of a particular phase, which is K over mu, multiplied by the BVT parameter like the oil formation volume factor. Last part is the potential difference, which is the nodal pressure minus bottom hole pressure minus the head. This is typically the basic simulation flow equation. So the approach is we have to define a reservoir realization. Realization means it's a set of fluid and rock properties combined together, plus the reservoir geometry and reservoir structure to define the reservoir architecture, the fault model, reservoir structure, fluid contacts, fluid properties like BVT parameters, the relative mobility and capillary pressure data, well completion, aquifer data, and so on. Next, you have plus reservoir realization, we have to define a development strategy. Development strategy means it's a combination of the schedule of the development plan of your field. How many wells will be drilled? What are the constraints of these wells, like bottom hole pressure, the surface injection pressure for water injection operations, subsurface data, and so on. So reservoir realization plus development strategy means a simulation case. So to highlight the model initialization process, it's as you can see in this 3D grid, this is the water saturation, as you can see, from SWI to 100%. So in the water zone, we have oil water contact at this level, and here this is the water zone, water aquifer, 100% water saturation, and here in the above the transition zone, we have clean oil production, which means we have oil plus SWI. But in between, for this transition zone in between, we have gradually change in saturation from 100% at this grid block to SWI at this one. And so to define this, the fluid distribution across this transition zone, this is the process of model initialization. So the commonly used approach for model initialization is the initialization by equilibration or by using the BVT and the fluid contact data. So in this case, let's say we have two different or three contacts: gas oil contact, oil water contact. And this is the free water level, which is the level at which the capillary pressure, oil water capillary pressure equals 0. So we have some transition zone between this free oil zone. This we need to define the fluid saturation, which is this one, and also we need to define the fluid saturation, which is this zone between gas and oil. So you have to define the fluid contact, this one and this one. You have to define a particular datum and the pressure at this datum, so you can calculate the pressure at any other point in this reservoir using this pressure gradient line. This is gradient line for oil, gradient line for water, and this is a pressure gradient line for the gas. The intersections between these two lines is the oil-water contact. In that case, we have to apply the rock physics and saturation functions to define the minimum and maximum saturation for each phase using the relative mobility curve, and to define the water saturation distribution using the capillary pressure curve. So these endpoints will be used to calculate initial saturation for each phase in each grid block, and the capillary pressure curve at any value of capillary pressure you can calculate or you can identify the corresponding water saturation, as you can see. So in this clean gas zone, we have no problem because we have gas saturation plus SWI. And oil zone, we have oil saturation plus SWI. But the problem will be in this area in between, or the transition, this zone in between this clean oil zone and the free water zone, as you can see. This is will be let's say at this depth, you can calculate the capillary pressure, oil water capillary pressure, using this equation. It will be this value minus this value, B oil minus BW. And then you can use the capillary pressure curve using the identified or the calculated capillary pressure in the first step to identify the corresponding water saturation. In the transition zone, it's not SWI, it's a value higher than SWI to reach typically SWI in the clean oil zone. Just an example, if you take an grid cell in this level, you can see SWI water saturation is 20%, which is SWI, and the capillary pressure is 6 bar, which is the maximum capillary pressure. And if you take another grid cell in this zone or the transition zone, we have water saturation is 0.28, which is not SWI, but here we have water saturation is 100%, and at the minimum capillary pressure may be negative. So how to define a simulation run? We have two main steps. First step is to define the development strategy, to define start the and end the data flow simulation case, to define wells and production constraints, and also historical or production data. Next step is to define a simulation case, to select the simulation grid, to define properties, and select the simulator. Mostly we have two common development strategy. The history strategy is to specify the actual well production and field performance, and try to mimic and match the historical performance by fine-tuning the model parameters, while the prediction strategy, after achieving a reliable history matching, can use the model in that case to predict the performance under different depletion strategies and economic rates and well drilling strategy and so on. So the simulation run, we have to define a 3D grid with particular properties. Rock physics function, as mentioned, development strategy may be history or prediction. Select the required simulation results, and you can finally select or activate some advanced features and controls in your model. Let's check on this model. As you can see, we have a 3D grid. So without going through in details of static modeling process, the first step, as mentioned for the model initialization, is to use the PVT and rock physics data to define the initial pressure and saturation for your grid block. But before this, you have to try, or you have to check and or quality check the reliability or the accuracy of your 3D grid by some tools to check the accuracy and the quality of your 3D grid. So, reservoir simulation, as mentioned, you have to define different realization or different scenarios for the data distribution, because we mostly have uncertainties in the subsurface data, because we have some controls at well locations like this point and this point and this one, but in between we have um, different levels of uncertainty in the data to define the data distribution between well locations. This is mostly the main uncertainty in reservoir simulation. So we have to define different realization, as mentioned, for rock types or fishes model. For porosity, as you can see, we have low case scenario, medium or maybe high case or best case scenario like this, and also for water saturation. All of this realization must be defined based on the degree of uncertainty for each corresponding case. For any questions, it will be at the end of this webinar. You will free to ask any questions. So, static modeling quality check, we have different tools like visual inspection for on 2D and 3D windows, like well sections, properties distribution using histogram, and data statistical analysis. Structural quality check, like the fault model, structure framework, and structure or 3D grid quality check, like to check the cell angle, to check the orthogonality of your cells, cell volume, to check how many or what is the value of the negative volumes we have in your 3D grid, and also check the cell inside out to check the distortions within one grid blocks or grid cell. Also layering versus actual data. Last step, you can check the gridding, grid type, grid orientation, numerical dispersion, and so on, without going through in details due to the time limit. So, visual inspections, like to display your model in different winds to check the data distribution. It's accepted to have distribution and porosity like this. We have only if you have geological justification for this distribution. If you have, let's say, an the positional environment, like a channel, sand channel, to have high porosity within this channel, and in between we have levee or flood plain. So it's common to see low porosity in between, like this purple colored grid cells. But in across the channel, we have the highest reservoir quality or the highest reservoir permeability. So no abrupt changes in values are accepted unless you have a geological justification or geological indications or evidence for such a change in distribution. Well sections, like to check the or to compare between the model properties against the input physical data or well logging data like this. This is very important. Also to check the top and bottom of your reservoir net base thickness, porosity, and permeability against let's say the core data or the physical data and so on. Oh, and next is to check the data distribution using this histogram to compare between the model porosity, for example, against the input porosity or the porosity from but physical data or porosity from the core data or conventional core analysis data. It's very important. So this is the visual inspection checklist. So this is very common. You can, in your models, you can check this is the water saturation distribution. You can display porosity distribution like this. So as mentioned, we have, if you display the fishes model, we have in this, we have a channel sand colored in yellow, and Levy sand in between. But we have right here in this gray color, we have background floodplain. It's uh, common to see this very low porosity in between. Also, you can check the data distribution using this option to check the yes, the statistical data for this property, and also check the histogram and compare this distribution against the bathyphysical data or against the conventional core data. Same must be applied for permeability, and we have permeability in IGK directions, and can be compared against the core permeability. And this is the distribution of permeability. As you can see, you can fine tune this histogram using this option to define the minimum and maximum value. Let's say keep it 10 as minimum value. So this is the permeability distribution, as you can see. Um, this is must be compared against, as mentioned, the input data from the well logging, or as you can see from the global well logs data. We have also velocity distribution like this from the input data, and this is the distribution of input velocity. So you have to compare between them. Also, you can display your data in well sections. Next step is to apply a quality check of the 3D grading process using some predefined parameters like the cell volume. This is the cell volume, as you can see. Let's let's yes, adjust the color scale. Yes. So for the bulk volume or cell volume in this model, yes, this is the cell volume. It's important to have minimum or minimal negative cell volume, and this is a distribution in this model, and also to check the as you can see, cell inside out. Also the cell angle. Cell angle is a very important property. Let's adjust the color scale to display. So cell angle showing the let's go to one slide right here. Yes. So cell angle is to check the orthogonality of your grid blocks or grid cells, because for the optimum grading process, the cell angle must be 90 degrees. We have clear or exactly orthogonal grid sides, but actually in real cases it's not. It will not be exactly 90 degrees, not exactly be orthogonal. So in this property, you can calculate the deviation in the cell angle from the 90 degrees, maybe higher than 90 degrees, maybe less. So the accepted value for the maximum cell angle is 15 degrees, which means 15 deviation from the orthogonal. It means it's accepted to have cell angle within 75 degrees as minimum value, and within 105 degrees as the maximum value. This is mostly will be associated at grid blocks or grid cells at fault locations. So in this model, as you can see, you can find the fault system. The cells with the maximum or the higher cell angle, as you can see, cell angle according to this color scale ranges from 0 to 90 degrees. So the majority of grid cells, we have cell angle almost 0, which means zero deviation from 90 degrees. But in this grid cells in contact with the fault, this fault or the fault model or the fault system, you have a change, or you have higher values of the cell angle. This is due to the grading process and due to the reservoir heterogeneity. So this is another quality check parameter. So displaying the fault model in this to check in this 3D grid to check. Yes, this is the fault model we have. If you apply a particular, yes, you can see right here the maximum cell angle. Let's display the histogram to check the cell angle. So maximum cell angle, as you can see, is almost 18 degrees. Almost the majority of data are less than 8 degrees. Almost, as you can see, 30% of the grid blocks or grid cells, you can change the incremental value, let's say 5. Yes, as you can see, almost 93% of your model grid cells have cell angle less than 5 degrees, as you can see, which is good and shows high quality grading process. This is a very important step why to check your 3D grid. Next property is, as mentioned before, this is the cell inside out to show how many distorted cells in your 3D grid. Let's check this one or this histogram. We have almost, as you can see, no distorted cell. This is a cell inside out. It will count how many cells are distorted. This is the cell angle, as you can see. Most of these are close to the fault model. Cell volume, as mentioned, shows the cells with negative volume due to the grading process and the reservoir heterogeneity and the complex fault model. And also you can check the fishes model and fishes distribution compared to the geological data or stratigraphical data like this. You can display the say the histogram of your fishes or your rock types. So in this histogram, we have 3 different rock types of 4 different codes: code 0, code 1, and code 2, corresponding to different, as mentioned, different depositional systems for the channel levee, and also the background flood plain. Yes. Yes, this is the 3 different codes: code 0 and code 1 is for the channel sand, which is the highest quality fishes in this model. So next is we have this is the STOIB quality check. So now I will highlight after the model 3D grid quality check using some tools. Now I will highlight the process how to define a development strategy. So development strategy, as mentioned, it can be performed in 2 different approaches. In the history strategy, it means we are applying a history matching to try to adjust to try to match the historical data or the actual production data. Second approach is the prediction strategy. This is once your model is matched and showing a reliable performance against the historical data, you can run the model in the prediction phase. First step is to select which simulator you need to apply or you need to use. Is it black oil simulator or compositional simulator or even advanced simulator? Next, in the development strategy, as mentioned, is to define the start and end date of your simulation. So starting from 1999 to the end of this run is 2005. And then you have to define the wells folder. You have to define also the for this folder of producers, and we have another folder of injectors. And for the history strategy, we have a very common rule, which is defined as history rate control. This is to check or to compare between the production volume from your simulator against the observed data. So observed data set must be defined. This is if you check the in wells folder, as you can see, we have this folder, which is global observed data. And the global observed data, we have up to or one observed data set like this. You can check the data using this spreadsheet. So the observed data, as you can see, we have data on the field level and data in well level like this. We have 4 injectors. Let's say we have one producer right here. So we have data against oil production, gas production, and bottom hole pressure. Other data may be available like gas oil ratio, like water cut, and so on. And for injectors, we have injection rate against the bottom hole pressure. This is mostly the observed data for this model. And we have another rule, which is the history pressure limit. This is to define the minimum and production bottom hole pressure and the maximum injection also bottom hole pressure for the wells. Once you define your development strategy, so next step is to define your simulation case. Definition of simulation case, as mentioned, you have to define basic. Yes, here you have to select which 3D grid to be used in this simulation case. Select the type of your reservoir modeling approach. Is it single porosity, which means this is the commonly used approach for conventional reservoir simulation, or the traditional simulation, or mostly for classic reservoir. For most of carbonates, you can the dual porosity or dual permeability models can be applied. In that case, you will assume the reservoir has 2 different elements: the matrix blocks with high storativity and high stored in place volume, and the fracture network, which is typically responsible for the fluid flow or the transmissibility of the fluid from the matrix blocks to the bottom of your wells. So the first important element in a simulation case is the grid. What is the 3D grid you have, and what are the basic grid properties as mentioned? The minimum grid data required are porosity and permeabilities in 3 directions, X direction, Y direction, and Z direction, plus additional data like net gross, like transmissibility and others. You can define all of these properties can be defined as you can see, like let me like to define the regions or active cell or act num to define the cell height, define SWC, SWI, as gas critical, and all of them to define even aquifer. Also, you can define water saturation and minimum proof volume. So different keywords can be added or defined in this grid section to define some constraints of your 3D run of your 3D model. In functions, as you can see, functions, it's similar to the shape of the relative permeability curve. So you have to check the shape of your relative mobility data and also the BVT data. This is the BVT parameters, as you can see, for oil formation volume factor. It's typical response like this. It's increasing from the initial pressure to reach the maximum value at the saturation pressure, then decreasing to reach value higher than 1. And for the oil density and oil viscosity, the behavior is mostly we have reduction in viscosity or even density from the initial pressure to reach the minimum value at saturation pressure at this point. And then due to the we have oil expansion without release of solution gas. But once the pressure is reached or less than the saturation pressure or the let's say the bubble point pressure, the gas in solution will start to release out of this liquid, which means the liquid becomes more heavier. So the oil density or oil viscosity will start increasing again below the saturation pressure. For the solution gas oil ratio, it's a constant value higher than the saturation pressure and then decreasing gradually to reach 0 at standard conditions, which means we have no gas in solution. To display also the rock physics data for like relative mobility and capillary pressure, you can display the saturation functions. So saturation functions, this is a composite saturation function plot, but you can select all of the saturation functions individually, like to display the, as you can see, this is the oil-water relative mobility curve. And also you can display the capillary pressure curve using like this. So this is the this is what will be required in the define simulation case. Let's back to this option. So in functions, you have to define the drainage relative mobility curves. Maybe you can apply single relative mobility curve for your model entirely, or you can apply different relative mobilities or different saturation functions, for example, for every fishes, as you can see, or every rock unit, or even you can define different saturation function in your for every segment. As you can see, let's check in this 3D grid how many segments we have. So we have this property, which is segment filter. So in this segment filter or segment geometrical property, we have 4 different segment or 4 different fault blocks or fault compartments. So you can define a separate relative mobility curve for each segment, as you can see. Otherwise, single relative mobility curve will be used for the entire model. Similarly, for the black oil BVT model, this is to define the BVT tables or even equation of state, plus the initial or the fluid contacts and initial conditions. Last thing is the rock compaction, to consider the reduction in the pore volume with the reservoir pressure while depletion. Next, we have the strategies to define your if you are applying a history matching run. In that case, we have to define this development strategy starting from 1999 to 2005. And next, you can select advanced options related to the simulation running controls, runtime options, transmissibilities, as you can see, to define, for example, minimum proof volume to try to minimize the convergence error for your simulation run, and another advanced options like partial export. Last step is to define what are the required 3D required simulation results for the summary vectors. Summary vector means we have XY plots like, for example, like the gas oil ratio versus time, water cut, oil production versus time, and so on. Initial 3D grid properties like as you can see, the grid dimensions in X direction, Y direction, Z direction, and so on. Recurrent 3D grid properties, they are time-dependent parameters, and also can define another options, another tools. And for the advanced, we have this option to highlight the structure of your simulation data file. As mentioned before, your data will be stored in different sections. Every section will have corresponding data related to the run specifications, like title of your run, start data. As you can see, if you double click on this file, you can find start date of your run is January 1999, and the available phases, the system of units in this model, it's a metric system. And for the grid, you have to define, as mentioned, the basic grid properties like Gaussian permeability. Solution section, as you can see, we have this keyword to initialize your model based on the equilibration approach, using the fluid gradient and the fluid the pressure at a particular datum plus the PVT and rock physics data. So once you finalize this, you can export your run to generate a data file, or you can run your case directly right here. Once your run is completed, you can display the simulation results on a charting window like this. So as you can see, we have right here the observed data. You can open this one to check the corresponding options. So what we are displaying right here, we are displaying the data of well before. We have bottom hole pressure versus time, gas production cumulative, gas oil ratio, water cut, oil production rate, and oil production cumulative. We have different sources of data. The initial data is the observed data, because this is the reference of our model. This is the actual or measured data, or the observed data. This data will be used as a reference to check the response of our model and fine-tune the model response to try to match this history. So this is the observed data colored in this one, and we have three different simulation cases. In this one, first one, case number one in the green color, it seems we have much mismatching between the simulation response and the observed data. Case number two, we have better matching. The response is mostly close to the observed data on bottom hole pressure, water cut, gas oil ratio, and so on. But case number three, we have the best performance of your model, which is typically matching the historical data. How to achieve this match in a case like this? Using the process of the uncertainty and optimization to define the response or the effect of the most uncertain parameter on reservoir response, and then you can fine tune this parameter, like change the permeability in X direction, in Y direction. You can also use the structural elements like the fault transmissibility and so on. So the sensitivity analysis study is summarized in this plot, like the tornado plot window or tornado chart. This chart showing the effect on different uncertainty parameters or sensitivity parameters, like the Curie exponent for the water, Curie exponent for gas, which means the most effective or the most influential parameter to achieve history matching for this model is the co-exponent, which is related to the relative permeability data or relative permeability to oil. Also, co-exponent for the water, this is the second parameter. So this plot is ranking the data from the most effective or the most influential one, followed by the one by one to the least influential one, which is the gas oil contact. So the gas oil contact has no effect on the model response. Last or third parameter is the oil water contact. The like endpoint KRW relative permeability to water at SOR or at the residual oil saturation. This is another important endpoint to affect the model response and so on. So this is mostly the quick workflow of simulation study or by the history matching, and then you can run prediction. Now I will highlight another model like this. This is a dual or naturally fractured reservoir, but the scenario right here is actually completely different, because in naturally fractured reservoir simulation we have the approach. As you can see, we assume the reservoir, this is the reality or the actual reservoir. We have fractured the reservoir, maybe carbonate or carbonate system with a particular depositional environment. We have a combination of the matrix, which is the bulk of the fluid storage, plus natural fraction network, and maybe we have dissolution bugs like this, especially in dolomite or dolomitic reservoir. So this is typically simulated by assuming the reservoir has two different porous media. The matrix block like this, which is responsible for the storage of fluid, and the friction network, which is representing the connecting channel between the matrix blocks and the bottom of the wells. So this system, the fluid, will be stored in two interconnected systems. The rock matrix to provide the bulk of reservoir volume, and the high permeable rock fractures like this in reality, and this is the simulator approximation. So this is typically the approach of dual porosity modeling. If we need to highlight the flow regimes and for the reservoirs, generally, if you have a homogeneous reservoir, it means we have one mobility and one storativity. So we have the fluid will coming from porous media to the bottom of the well through well completion. But if you have dual porosity system, in that case, we have two elements. The only porosity one, as you can see, we have matrix blocks and we have fractures, but the assumption is the fracture network is only connected to the wells, but no direct communication between the matrix blocks and wells. So the flow will be will coming from the matrix blocks number two to the fracture network, and then the flow will be from the fracture network to the bottom of the wells. This is typically the dual porosity systems. Meanwhile, the dual permeability assumes we have direct communication between the matrix blocks, and also we can find a fluid flow directly from the matrix to the well bore, and also from the fracture to the well bore. This is typically the concept of the dual, or the difference between dual porosity and dual permeability systems. So in the reservoir simulation, dual porosity modeling means we have two simulation cells associated with each block in your 3D grid, representing the matrix and the fracture network. In that case, we have a fracture matrix fracture coupling transmissibility, which is defined as sigma factor to link between the matrix blocks and the fracture network. And as mentioned before, the matrix blocks are linked only through the fracture system, which means no direct communication between matrix blocks to the well bore or bottom of your well completion. Meanwhile, the dual porosity, dual mobility, in that case, we have a possibility of flow directly between matrix blocks itself. So we have, as mentioned, this is the transmissibility in the dual porosity system. We have this equation, and this term is defined as the sigma factor, or matrix fracture coupling factor. This factor has dimension of L to the power -2, because it's defined as per this equation in terms of 1 divided by Lx squared, Ly squared, Lz squared. This is mostly in dual porosity simulation used as history matching parameters, because you will fine tune the value of this parameter to try to match your historical data. This is typically the commonly used approach. So, and without going through in details in the driving mechanism, I will skip this. But you have to keep in mind, for the dual porosity reservoir simulation, we have two different saturation functions, which means you will define separate relative mobility and capillary pressure for the matrix blocks, and another relative mobility and capillary pressure for the fracture network. Mostly in reservoir simulation, for fracture, we will apply straight line relative mobility like this, which means the endpoints of SWI will be 0, is maximum KRW will be 1, SOR will be also 0, and KRO at SWI will be 1 as well. This is the straight line relative mobility for fracture. Also, for the fracture, you will apply capillary pressure as 0, because we have the size of fracture network is much bigger compared to the matrix blocks. So you will ignore the effect of the capillary pressure. So without going through in the fracture modeling approaches, we have different techniques. The widely used one is this one, discrete fracture network approach. But once you finalize this process, to define a simulation case for dual porosity, dual permeability system, in that case, as you can see, you have to define separate parameters or properties for the metrics like porosity, permeability, net growth. For the metrics, we have this option, it's for fracture, no, but we have also another parameters only for the fraction network. This option, we have BIM X, BIM I, JK, and also porosity. This is only for the fraction network. In between, we have to link between metrics and fraction using this sigma factor or matrix fracture coupling transmissibility. For this model, we have corresponding or different keywords related to this model. So back to this model, as you can see, let's check on the, we have, this is the relative mobility data. And the blue color, this is the relative mobility for the fraction network as a straight line. While in the red color, this is the relative mobility will be used for the matrix blocks. Also, if you look at the 3D grid, we have the porosity for matrix mobility, also for the matrix blocks like this. While for the fractures, we have another porosity highlighted by this one, which is much better, much less than the porosity in the matrix, but permeability of the fractures like this one. This is fracture permeability, as you can see. Let's check on the histogram. Like this is it's very high permeability for the fracture network compared to the permeability of the matrix like this. As you can see, this is the permeability of matrix in horizontal direction, permeability in X and Y direction, as you can see. Compared to the permeability of the fraction network, it's for fracture, it's very high because the fracture system is responsible for the fluid transmissibility between matrix and well completion. To highlight the development strategy for such system and the simulation case, let's as highlighted before in the grid section we have right here, we have additional options are active right now, but you have to check at first as a first step the model type is dual permeability, which means the we have two elements, matrix blocks and the fracture network. You can find direct fluid flow from matrix to fractures, and also direct flow between the matrix blocks themselves. This is simply the approach of dual permeability modeling. So for we have defined permeability and porosity and also net growth for matrix, and here we have this for fractures, and we have this factor which is sigma matrix fracture coupling factor. For functions, you will find additional functions. This is the drainage relative mobility. This is for matrix. Another relative mobility is defined right here. This is the for the fracture system. Also, you can define different BVT models for matrix and fractures and so on. Or mostly the same BVT model can be applied for all of them. Otherwise, the strategies will be the same. Other options and results will be the same. You can check also in the in your data file. In this run spec section, you can find additional keywords like this one, dual burn. This keyword will be used to activate or to initialize the, as you can see, as per this description, to run your or to activate, as you can see, the dual mobility option in your 3D grid. Another options or another keywords will be added right here in the grid section, and also prop section and so on, to define the corresponding properties of the matrix blocks and fracture network. Once you finalize this, you can run your model and display the simulation results like this in well models or in well level or even the field level and so on. So this is the mostly we have right here some of keywords related to the dual velocity and dual mobility system or simulation, and their corresponding section in your model data file, as you can see, as a summary. So that's all I have. Thank you so much for joining this webinar, and now feel free to ask any questions or clarifications.
Thank you, Engineer Hisham, for this wonderful session. Now it's time to receive the attendees' question. Please type your question in the chat box, and Engineer Hisham will answer shortly. Thank you.
I think I have an old question. Is it possible to share this and the data used was betrayal? I think the presentation will be shared as an overview shortly. But for the data, it's can be shared individually. It's not public data. For any technical questions, please go ahead. We have a question: are data science approaches now more dominating versus traditional reservoir simulation? Data science, you mean the machine learning and artificial intelligence? Yes, even applied in reservoir simulation in approaches like the assisted history matching, like improving the history matching of your simulation models. But actually, these techniques will not totally replace the traditional approach of reservoir simulation. They can be used partially in some parts for the using the artificial intelligence techniques for geology and geoscience, for biophysical modeling and data distribution, and also for the history matching or assisted history matching, as mentioned before. Also, they can be applied in the and some the statistical analysis and production data analysis and production even production forecasting and so on. But at the same time, the conventional or the numerical approach is still used so far with high degree of confidence and high degree of the data accuracy. So can use we have a question which software can please you can also you can only ask for any technical questions. We have in the market, we have different simulators without mentioning some, without any specific one, but you have in oil and gas industry and oil and gas market today, we have different commercial simulators, maybe applicable for one options, maybe one valid for the complex models, like advanced simulator. We can be applied for enhanced recovery techniques and so on. Each simulator has a particular powerful option, maybe related to enhanced recovery, second recovery, higher dual prosthesis systems, dual mobility, and so on. So we have variety of simulator with different differences in the options and differences in the capabilities of every one of them. Um, so can we estimate the volume and how much merge of uncertainty and risk for investors? Mostly to highlight the approach of uncertainty for in volume calculations or even in the simulation results. You can provide different scenarios with a corresponding degree of uncertainty, which means you can apply what we call the stochastic approach, for example, for the in-place volume to display how much oil is expected at 90% probability, how much oil at 50% probability, and 10% probability, and so on. This is typically the commonly used approach in to highlight the degree of uncertainty. Um, can software be used to determine the amount of oil in? Yes, this is to calculate how much oil is originally in place. This is the actually the initial application of for any simulation model is to calculate the in place volume and to compare this volume with other techniques like the volumetric calculations, like material balance equation, and so on. To reduce the histomatching matching time, use advanced option in development strategy. Yes, we have um, some options to it's not histomatching matching time, is to minimize the running time, not the histomatching matching time, is to minimize the running time of your model. To minimize the histomatching matching time is in that case you can apply the uncertainty and optimization approaches to identify the most, as we highlighted before, to identify the most influential or the most effective parameter in the simulation results. That's once you identify these parameters, you can directly fine-tune these parameters to achieve matching versus the historical data, and accordingly you can minimize or reduce the histomatching matching time. Another question, can we use it to determine water resources and used in water prospection? Water resources, it's not clear what does it mean by water resources. Uh, Especially for geological model. Yes, the simulation modeling, as mentioned before, is performed using two major steps: static modeling or geology and geophysics to build the 3D grid using geological and geophysical and also the geoscience data and physical data to highlight the data distribution across the 3D grid. Second phase is the dynamic modeling by introducing the PVT data and the historical data, and also the rock physics functions or saturation functions like relative mobility and the capillary pressure. So what is the difference between MBL and software for determining in place volumes? We have generally, material balance analysis is an analytical approach to identify how much oil is in place. As mentioned in this approach, we have some assumptions like in material balance analysis, you assume you have constant porosity, you have constant water saturation, the pressure is averaged throughout the entire reservoir, which is not reliable because in real cases we have changes or distribution in on all of these properties throughout the entire reservoir. But the main or the critical issue regarding material balance analysis is to have accurate production data like pressures, static reservoir or static reservoir pressure and production data. In that case, you can achieve good results from material balance analysis. On the other hand, the numerical approaches like reservoir simulation, uh, the the calculated volumes will be more realistic if you have more reliable and accurate grading, accurate 3D grid, accurate engineering data like BVT and fluid contacts, and also the saturation functions and so on. So the comparison between them is it's not simple, but some technique has good results in some cases and the other is better and so on. It's not straightforward, but generally results on from reservoir simulation and material balance must be close within plus or minus 5%. This is the accepted difference between the in-place volume from material balance and reservoir simulation. Another question, water resources is subsurface, as we know that possible to make model for water saturation, and the question, can we make models using yes, in that case this is related to the petrophysical modeling generally, and the water saturation distribution. This is yes applicable in this in our 3D model. Any other questions?
I think this is all for today. Thank you, Engineer Sham, for answering all these questions. Here's also a kind reminder that our next live course titled Advanced Practical Reservoir Simulation will start this Sunday. It will be conducted by Engineer Hisham, the same instructor of today's webinar. So make sure you contact us to enroll in this awesome course. We have one last question. What
Uh,
PVT and log data do
yes.
we need to run the numerical reservoir simulation?
Yes. Basic PVT parameters, as mentioned, they are the if you define a black oil model, in that case, oil formation volume factor, solution gas oil ratio, and oil viscosity. This is the and also oil density. This is the minimum PVT data required for a black oil model. For the rock data or defined rock physics function or saturation functions, the minimum data are the relative permeability, at least for oil water system, oil water relative permeability curve, plus the oil water capillary pressure curve. All of these data are required for running your model and also for model initialization to identify the initial pressures and saturations for each grid block at the initial time step. I think there is no more questions. Thank you so much for joining this one, and see you in the upcoming events. Thank you.
Thank you, Engineer Hisham.